summary slide here. Let's just kind of go through the stuff we learned in Chapter 2. Whew, there's a good amount in here. So, let's look. In the top left, we have our linear resistor values with our resistance equals PL over A. And we also have the equation for power equals current squared times R. Power equals voltage times current, and if you change V equals IR and substitute that in, you're going to get power equals I squared R, any of the other combinations that might be useful or relevant to you. Kirchhoff's current law essentially is saying that if you pick a node, the currents coming into the node have to equal the currents coming out of the node. Kirchhoff's voltage law is saying that in any given loop that you go through, the sum of the voltages has to equal 0. For resistor combinations, in series resistors, you just add them up. A 3 ohm resistor in series with a 1 ohm resistor, 3 plus 1 is 4 ohms, and you can make a new resistor with a total equivalence. Parallel resistors, add the reciprocal. So if there's a 3 ohm resistor and a 1 ohm resistor in parallel, 1 over 3 plus 1 over 1, get the sum of that, and then bring it up to the minus 1. G down there is the conductance, which is the opposite of resistance. We're going to ignore that for now. As long as you know how to calculate resistors in parallel and what resistance is, conductance, remember, is just essentially the reciprocal of it. We don't use it too much in electrical. We use resistance instead. So, top right, voltage division. So if I have a power supply Vs and I have 2 resistors in series, they are going to divide the voltage between them. You can think of it as a percentage. And the equation right there is essentially how much of the voltage is going through the top one versus the bottom one. So that's a basic voltage divider. If you go down one, a current divider, if you have a current source and you have 2 resistors, that is the basic equation for current divider, which is R2 over the sum of R1, R2. And if you have more resistors in parallel, this also works as well. You just take the sum of all of the parallel resistors on the denominator. If you see the G1 and the GEQ and the IS there, that's for conductance, which is essentially the reciprocal again of resistance. If we look down underneath that for source transformation, a voltage source with a resistor directly in series with it can be transformed into a current source with a resistor in parallel, and vice versa. You can go back and forth. This is important sometimes because sometimes we're going to get current sources and we're not going to know exactly how to solve that directly off the bat, but if we can translate it into and transform it into a voltage source with a resistor in series with it, makes it much easier to solve. The next bit, we have a Y to delta transformation, table 2.5. We've done a bunch of problems on this. You should be solid on this. This is really important. You need to know it. And then also we have the Wheatstone bridge, which, again, we solved a couple of these in class. And there's the basic equation for the Wheatstone bridge if it's been balanced properly. V out equals V0 over 4, and then the change in resistance over R. And again, we're going to have some lab materials to go with that as well to kind of knock the Wheatstone bridge out and really understand how it works. But essentially this is a lot of information for Chapter 2. Let me know what questions you have. We're going to do a couple more problem sets. If you have any questions for me, ask, or the TA, and we're going to knock these out, and that way we can get onto some cooler and more interesting circuits. All right, guys, good luck. Bye-bye.